First, I would like to thank Irfan for this great conference and for inviting me to come here. And it's a real pleasure to come here for the celebration of John Clarke's achievements. I have known him since the mid-70s, perhaps longer than most of you, and it was the times of non-equilibrium superconductivity, which I did in my PhD work together with Albert Schmidt. And then I got to know John better when he spent his sabbatical in Karlsruhe. That was in '78. And we worked together, we wrote papers together, and we explored the wine scenery in Germany. There's also good white wine in Germany, and we went to the Pfalz and to a very good winery. And the contact continued. Let's say our interest also evolved in the same direction. So there was the time of the macroscopic quantum effects in Josephson junctions, and I saw the great work which was done here in Berkeley, which then evolved into superconducting qubits, and then the natural question, what are the noise sources, what is causing the decoherence, and we have been working together again in the last few years on those issues. So it was great to see John. I'm happy to be a friend of him, and so I'm happy to celebrate with him. My talk is a bit more technical perhaps than most of the other ones. And I will talk also about a certain noise source, namely the noise which arises from two-level defects which have a dipole moment, electric dipole moment in the material. And let's say actually my talk has perhaps two titles. Now let me get accustomed to it. Yeah, it has two titles. The first one, and I will first report experiments where Josephson qubits have been used as a probe, as a tool to study the properties of these two-level systems which are known to exist in materials. And then in the end, we will see that these two-level systems themselves suffer from decoherence. And the question was, what was causing the decoherence for these two-level systems? And that's where the spectral diffusion part comes in. It's work done together with experimentalists in Karlsruhe. It's the group of Alexei Ustinov, and in particular of Jürgen Liesenfeld. And also on the theory side, it's a collaboration together with a group at Ben Gurion University, Moshe Schechter and his student, and in Karlsruhe with Sascha Schneermann and students in my group. Okay, now two-level systems have been studied for half a century, more or less. They exist in all solids and show up prominently at low temperatures and influence the low temperature properties of solids. They are a source of noise for qubits and a nuisance. But then on the other hand, we can now use the qubits to study these properties of these two-level systems. And that has been done already. Let's say there has been some earlier work in Alexei Ustinov's group. But now, and here you see this. Here you can study them, and what you see here is the level spacing of two-level systems which exist in an oxide in a tunnel junction, and they depend on strain. And I'll explain a little more how this comes about as I go on, but I already wanted to explain this picture. Now, in addition to just looking at the level spacing, now Jürgen Liesenfeld has studied the dynamics of those two-level systems. They are two-level systems like qubits themselves. They have relaxation with the time t1, and they have decoherence with the time t2. And so he studied this dynamics, and this is what I'm going to report about. And then, as I said, the question was, what is the origin of the noise influencing these two-level systems? So, let's say these two-level systems, as I said, exist in the oxide of a tunnel junction. And after 50 years of studying these two-level systems, we know they are there. We know many properties, and I will summarize them as I go on. But we still don't know what is their microscopic origin. But let's say somehow the hope is that by continuing studying them, we will eventually learn more about that, and then perhaps eventually know how to avoid them. And here a short indication. I mean, the qubit which was used in those experiments is a phase qubit. Apparently it works. It's a phase qubit. I don't have to explain here properties of the phase qubit, but I want to shortly indicate this logo here, the protocol, how you use the qubit to study these two-level systems. It indicates here that you drive your qubit, perform a pi junction, so you bring your qubit into an excited state. Then you tune the qubit to the frequency of the two-level system. That means you search for it, but if you successfully tuned them to resonance, then a swap operation will happen. The two-level system is in the ground state and the qubit was in the up state, and then you swap. If you do it the right time, you have to tune all these parameters. Then you have your qubit back in the ground state, and if you then do a measurement of this phase qubit in the usual way, then you find it was in the ground state, and hence you know you successfully found a two-level system. And by doing this, Jürgen Liesenfeld and co-workers produced this picture. And what you see here is there are many, not infinitely many, but there are many two-level systems in this particular setup. You see there's a characteristic dependence on the strain which is applied, mechanical strain. And we will go on and study more of them. Okay, as I perhaps said already, there was earlier work in the group of Alexei Ustinov who found this spectrum already, and Jürgen Liesenfeld did it with this protocol which I explained and continued from there. Now there's something called the standard model of two-level systems, and it consists of two parts. One part I explain now. There are two-level systems, so we know we can describe them by Pauli matrices. There's a bare level spacing and a tunnel coupling, delta, and let's say it's then usual to go to the eigenbasis of this two-level system, and I call this Pauli matrix in the eigenbasis tau. This is important for when I go on. And the level spacing, then what we have seen before, depends on both the bare level spacing and the tunnel coupling. Now, these parameters epsilon and delta are distributed according to some distribution. The standard model assumes that all epsilons are equally likely, so the distribution does not depend on epsilon, but large deltas get less likely. So this is the standard model, which is also underlying this Data-Horn theory for 1/f fluctuations. And P0 is a material-dependent parameter. If we now apply some strain, I mean, all they are coupling they are electric dipoles, so if you apply some strain, you influence the bare level spacing in this way here. It's actually a rather strong coupling. The energy scale which enters here is an electron volt, and this is the strain, the change in the length of the system. And now, so after you see this dependence on the strain, which enters into this energy, you understand this hyperbolic shape of the energy spacing, which has been seen in the experiment. Now we know they are there, we know their frequencies, we know many properties like how strongly they couple to the qubit and so forth, and now one can do all the zoo of dynamic experiments. One can perform Rabi driving by directly coupling to this two-level system. We take a specific two-level system, we know its frequency, we drive the system by microwaves and do Rabi drive oscillations. We can excite the two-level system by applying a pi pulse and then watch how it relaxes to the ground state again. We can do the usual Ramsey or echo type experiments to measure the coherence types. And these are the results which Liesenfeld et al. Obtained. So the first panel here shows the Rabi oscillation. So now again the logo means you are driving the two-level system for some time, and then it should do the Rabi oscillation. And after some time, you do the measurement by tuning the qubit to a resonance with the two-level system, have the swap operation, you know now how strongly they couple, and afterwards measure the qubit. And so what you see is Rabi oscillations, not perfect, not beautiful ones, but rather well-developed Rabi oscillations. And you see that red data and blue data. Red data are at the minimum of these hyperbolas which you saw before, at the symmetry point, and the blue data are away from it, and we will see there's a sweet spot. So the system is particularly good at the symmetry point and not so good further away. Then the next panel shows the relaxation after you excited the two-level system and measured it by the qubit, and you see a characteristic decay. You see the time scale for the relaxation is of the order of a few microseconds. The panel C shows the Ramsey fringes. You see coherent oscillations. Now again, you see a big difference between the coherent oscillations at the symmetry point, and if you move away, the decoherence is much stronger. And finally, here you see the time scale for the echo experiment. Okay. Now here, a bit busy picture, but I'll go through it in some detail. So in the first panel, you see 4 of those two-level systems, of which you saw many more before, are now selected. Each one, we look at them in the vicinity of their symmetry point, and the axis down here is the deviation from the symmetry point. And then the first panel shows the relaxation time, T1 time, as extracted from the picture which I showed before, as how it depends on this separation from the symmetry point. The panel C shows the decoherence time in the Ramsey experiment or in the echo experiment in blue and green, and also for comparison 2 times T1, which is good because when we want to have the pure dephasing in the Ramsey or echo protocol, we should subtract from the measured T1 and T2 inverse the rates, we should subtract 1 over 2 T1. And this is then plotted in the last panel, which looks a bit now more transparent. Let's say, look at this one you see here. This is the decoherence rate in the Ramsey experiment in blue. And if you do an echo experiment, you see the decoherence rate in the echo, and it's obviously much smaller. And that you see for the 4 examples up there. What we see here is a characteristic energy dependence, how it depends on the distance from the symmetry point. Okay, now what would be the standard theory? Well, we usually know, I mean, there is a fluctuating field phi, and it couples to the dipole moment of these two-level systems. But we have to go to the eigenbasis, and then this fluctuating field couples to induces transitions via tau x, or it shifts the energies via tau z. And then, let's say, for the relaxation, we do per golden rule. We get the relaxation rate, the usual standard result. It has a characteristic. I mean, this prefactor delta over EP appears squared, and we need the power spectrum at the frequency of this two-level system. And now, if you look at what we have seen up there, you see there's a lot of structure. We don't see any trace anymore of this delta over EP squared. And what the experimentalists concluded at this point is that the relaxation is caused by a coupling to phonons, and the phonons in this restricted geometry have a structured spectrum, and that is what they conclude is the source of this relaxation. It's not my main issue now, so let's just accept it. We have now measured T1, and probably it is caused by interaction with phonons. Now, then the Ramsey and the echo experiment, the results are shown here again. And let's say the naive theory, the standard theory would say it's this part which is causing the decoherence. And again, golden rule type arguments, we expect a decoherence rate, this is the pure dephasing rate. Usually it has a star, but the experimentalist didn't put a star, so I didn't put it either. So the pure dephasing rate would be given by the power spectrum at low frequencies. And because of this transformation, we have an energy dependence, which is indicated here. Of course, the total, it's related. I mean, as I said, in order to get from, we get this reduced data, I said it already, by subtracting the 1 over 2 T1. Now, when we look at it now, what do we notice? Well, first of all, we notice that at least indeed at the symmetry point, the pure dephasing rate vanishes. So this sweet spot strategy works well also for these two-level systems. We see a huge difference, partially, not so much here, but in some cases, a huge difference between the Ramsey decoherence rate and the echo decoherence rate. So the echo is very efficient here, still very efficient in the other two. But one thing is not looking right. You see, I would expect an epsilon squared dependence, a parabolic dependence also for the Ramsey experiment, and we see the experiment shows it's a linear dependence. This Ramsey dephasing rate goes linear in the epsilon, not like epsilon squared, what I would expect from here. So what we conclude at this stage is that the simple theory does not fit to the data. And that raises now the question, so what is causing the decoherence of these two-level fluctuators? And that is actually now my main part of my talk. Now the message is, it's other two-level fluctuators. And now we have three types of two-level systems in our system. We have these two-level systems which we probe via a qubit, and there's a finite number of them. We looked at 4 so far. And we look at them by tuning our qubit to resonance with these probed two-level fluctuators. And what I will argue is that the decoherence of these two-level fluctuators comes by interaction with further two-level systems, low-frequency two-level systems, which behave like classical telegraph fluctuators, and that at low frequencies they are oscillating, and this leads to this decoherence of the probed two-level systems. Okay, now a little more about the standard theory of the two-level systems. What is also known is that they interact with each other, with the dipole moments interact, and the interaction, which is mediated by phonons, decays like 1 over the distance cube. We have further some feeling for what is the density of these two-level systems. The typical spacing would be a nanometer, and then the typical coupling strength would be rather high, something like 20 gigahertz. And what the community, those physicists who have been studying these systems for a long time, they tell us there is a universal property, like the universal flux noise of John Clark, and here I see the connection. There's a universal property that this parameter P0, which we saw in one of the earlier slides for the distribution of epsilons and deltas, and this interaction strength, the distance dependence just cancels out here, is 10 to the minus 3. And so this is basically, now we have the only input which we use for the following analysis is a typical spacing of a nanometer, and then the universal number gives us the remaining parameters. Now, there are many. You see, it's a high density of 1 per nanometer cube, but most of them have a high energy. And at low temperatures, where the experiment is performed, where it says somewhere 35 millikelvins, at 35 millikelvins, most of these two-level systems don't move. They are in their ground state. Only a small fraction of them, the thermal two-level systems, those with energy smaller of the order of kT, only they will fluctuate frequently, and only they are responsible for the noise which we see. Now, just from the numbers which I gave you, we can immediately then find what is their fraction, those with smaller energies, and they have a typical distance of 20 nanometers and a typical coupling strength of 10 megahertz, and they switch due to the interaction with phonons, again something which we know took from the literature, so to speak, and we know that they switch at a rate which is the maximum switching rate is of the order of 10 kilohertz at these low temperatures. And that explains now the picture up there. We have many two-level systems, but the black ones are dead. They don't move. The red ones are the ones which are causing the noise, and they have these typical parameters which I show here. And they influence the probed two-level system, which is shown in blue here. And there's a typical distance and these 20 nanometers, which I showed here. Okay, so now the question is, now we have these two-level fluctuators. And then what does a two-level fluctuator do to, now I use the two words, two-level fluctuator for those thermal ones, which fluctuate like classical telegraph noise, and they influence the properties of our quantum two-level systems. And so we have to understand, and it's what I show here, the results are known, how does such a telegraph noise fluctuator influence a qubit, or in this case now the two-level system. So this is the model which we have here. We couple in the eigenbasis of this two-level system now, we have a fluctuating field which switches, has two values, plus or minus v, and switches with the rate gamma. And then we calculate in the usual way, the decay of the coherence is described by this function f, which is the average of this phase which evolves due to this fluctuating quantity. And there's a an analytic result for these decay functions. It looks a bit messy, so we found it useful to look at various limits, and what interests us mostly is the limit where the frequency is smaller than the coupling, and then we have still short and long time behavior for the Ramsey and the echo experiment. Now, next thing we have to do is we have many of those. So we have to now average over all the two-level systems. Also we have to translate how the dipole-dipole coupling translates into a coupling in the eigenbasis of these systems. So if there's another epsilon over E coming in for both. We have this decay as a function of distance, which I mentioned before. And so now what we do is basically just average these complicated expressions which I showed before, and we get average both over all the distances and the distribution of this P of epsilons, distribution of the epsilon and delta, which I showed in the first slide. Okay, so we have done it. Oops, yeah, I skipped that. And with the following result, that this average result leads to an exponential decay which depends on the epsilon p magnitude and the parameter jt, which I identified before. This is the average result. Now, things get a little more complicated. We realize that the average result is probably not what is seen in the experiment, because we understand that the average result is very much dominated by very close by two-level fluctuators. The experimentalists wouldn't have looked at such data. If they look more at the typical data, so in the typical data, we don't have to do the averaging, we just take the typical values and we get this result. So we get an e to the minus t squared decay. Now, unfortunately, at this stage, the experiments don't, in principle, you should be able to distinguish in an experiment whether it's a simple exponential or e to the minus t squared decay, but the data don't allow us this, to decide what is the result. However, the good news is both have the same time scale for the decay. You see in both cases the rate for decay is given by jt times epsilon magnitude over ep, and this is what you see is what we have seen before in the experiment. It is this linear epsilon p dependence which we get here, and I assure you also the magnitude of the effect fits to the experiments. And this is actually my main result. My main result is that the standard model without fitting explains when we, with this, after we understood how it couples, gives this linear dependence. Next thing is we go to the echo protocol, and so we can do, in this case we can average, and we get a dephasing rate in the echo protocol, which is much lower than the Ramsey dephasing rate. So no surprise perhaps, I mean we assume these are slow two-level fluctuators. Obviously we very efficiently can eliminate the effect by echo techniques. And then again we look at the experiments. And well, first of all, what we notice is that if it would be only these two-level fluctuators, we should have basically no echo decoherence anymore, something like what you see on the right. But we still have some, in most cases, we still have an echo signal. And it goes like epsilon p squared, as we saw before, as we would find in a simple theory, whereas now these two-level fluctuators, they still have a remaining decoherence also in an echo experiment, but it would not go like epsilon p squared, but like a square root. So what we conclude is, in the echo experiment, we don't see any effect anymore of those two-level fluctuators. They are very efficiently removed. And what we see in an experiment must have some different origin with a more wide spectrum for which the simple theory, which I described before, applies. Now, my time is coming to an end. We have speculated about it. There are two ideas how this remaining decoherence, what is the source of this remaining decoherence? It could be quasi-particles. They are there. They do play a role. They do give a right order of magnitude. But let's say we wouldn't understand the strong variation from in the four examples. Moshe Schechter thinks that it's somehow specific, strongly coupling two-level fluctuators which do it, and there are few of them, and so the spacing to the probe two-level fluctuator varies a lot. That could be an alternative explanation. But both, I don't want to go into detail now. I want to summarize. So we have seen that we have a nice application. Josephson qubit is good to study these two-level fluctuators, and perhaps it helps us to understand their microscopic origin eventually, and then eventually how to avoid them. The main result was that the Ramsey experiment is quantitatively explained by the standard model of two-level fluctuators. And we have the echo experiment, and the T1 relaxation relies on other sources of fluctuating fields, like the phonons in one case, or the open question, which I mentioned at the end. Thank you very much.
Questions?
So what is the density of two-level fluctuators at low frequencies? It looked like it was sort of constant down to...
Let's say the active ones, those with a low frequency, are 20 nanometer separation typically. So there are many more, but they are not active anymore. At the low temperatures where the experiments have been performed. Yeah.
So I just wanted to make a comment and maybe get your sense of this. It's amazing, results to be able to see these individual two-level systems and measure some of their properties. And it must also be frustrating, and it certainly has been for us, to not know what they are. That's a remarkable thing. Sort of. It's we're clearly missing.
Let's say I can say, I mean, certainly in Karlsruhe, it stimulated activities in this direction. So like looking at it in a microscopic, say, do a different growth, look at it in an electron microscope. We have some ideas that let's say the natural thing would be it's perhaps just one electron hopping around. Somehow the feeling of the experimentalists is it is more like somehow a small cluster moving between two different positions. Only then you get the right frequencies and so forth. So we are working on it. It's challenging here.
Could you elaborate? Could you elaborate on the experimental part as well a little bit?
Elaborate on which part?
On the experimental part, as to how the experiment, where was the strain applied for this experiment?
I still didn't understand your question. Please repeat.
I thought in the beginning you showed that there was a strain being applied.
Oh, the strain. Oh, yeah, the strain is basically just, externally with the piezo. It's a bit similar to this break junction bending, which we saw before. You apply a piezo.
On the entire qubit?
Yes, it's somehow a planar structure, and you get some strain on
okay,
of
thank
it.
You.
Yeah. But it's a piezo which they drive and then see how it moves. Yeah.
Any further questions? Okay, well, let's thank Gert again.
Thank you.